Hello, everybody. Today, we're going to talk about the probability objective in Math 105. To do that, let's look at the following. Let's suppose we have these grades right here, and let's find the probability of a student having a grade of A. Here we have this table of information about grades. So here we can see that 3 people had a grade of A, 5 people had a grade of B, 8 people had a grade of C, 3 people have a grade of D, and 2 people have a grade of F. So given this table of information, we would like to know what is the probability of a student having a grade of A. Well, to do that, before we figure this out, let's talk about some terminology. So any sequence of words after the words probability of is called an event. So in this case, a student having a grade of A is the event. So what we can do is let a variable represent that. So let's let the variable A equal a student having a grade of A. To find the probability of, we have this terminology called P of A. Now, recall that in another video we talked about functions. A function has the format of f parentheses x, and even though this looks like f times x, this is really the function f of x. Well, instead of f of x, we have here what's called P of A. And P of A is a kind of function that represents the probability of A happening. So again, P of A represents the probability, since P stands for probability. So we have the probability of the event A happening. And to find that probability, notice that we're talking about the probability of picking a student. A student is just one student. And so anytime you want to find the probability of picking just one thing or one item, then we make a fraction. And in the numerator, we put how many is involved in the event. Now, even though we're picking just one student, the numerator is not going to be 1 because that's how many we're picking, but instead, the numerator is how many totally we have in the given event. So in this case, since the event is a student having a grade of A, in the numerator, we put how many students actually have a grade of A. And that would be 3 students. So we'll put 3 right here in the numerator. In the denominator, we're going to put the total of everybody. So we have the total of all these students. So if you do that, let's see, we have a 3 plus 5 plus 8 plus 3 plus 2. So that's going to be 21. So the denominator is 21. So the probability of picking a student having a grade of A is 3 over 21. And this reduces to 1 over 7. So let's do another example. Let's find the probability of a student, or technically we're going to pick a student, find the probability of picking a student who has a grade of C. Okay, now same thing. We can let the event, some event stand for, or we can let a variable represent the event. So in this case, the event would be, again, everything after the words picking of. I'm sorry, the event is the event are all the words after the words probability of. And we have picking a student who has a grade of C after the words probability of. And so we'll let the event, in this case, we can say B is equal to picking a student who has a grade of C. And so we'll denote this by writing P of B. So in this case, P of B stands for the probability of picking a student who has a grade of C. And again, we'll do the same kind of idea. We're going to count up how many people have a grade of C. That's 8. That's going to be 8 over 21, the total. And that already reduces as 8 over 21. Now, we can write the probability in terms of any form we want, whether it be a fraction or a decimal or Braille or the Japanese kanji, however you like to write it, it doesn't really matter as long as you have the right answer. So in this case, let's convert it to, say, percent. So 8 over 21 is approximately going to be, we'll say 38.1%. And so technically this means that out of all the students, 38.1% of them have a grade of C. And so to find the probability of picking just one thing, whether it be like one student or one rock or one hamburger or one fry, all we're really doing is just finding out what percent of the entire total of them make up those things. So in this case, since we're picking a student who has a grade of C, the probability is 38.1% approximately. So this just simply means out of all the people in the class, about 38.1% of them have a C. Now, let's find the probability of picking a student with a grade of E. Right now, we could write out the terminology with the A and the P of A, that kind of stuff, but let's just dive right into the answer for now. So to get the answer again, just make a fraction line. And this time in the numerator, we want to put how many students have a grade of E. Well, if you recall, there's, according to the table, there's no students with E, is there? And so it's going to be 0 over a total of 21. 0 over 21 is 0. So the probability of picking a student with a grade of E is 0. That just simply means that it's impossible to find a student with a grade of E. And so if the probability of an event is 0, that means that event is impossible. Now let's find the probability of picking a student. Well, in this case, we're not limited to whether the student has an A or a B or whatever grade. We just want to pick a student. Well, there's going to be 21 students, right? Out of a total of 21. So 21 over 21 is 1. So the probability of picking a student is 1. Now, assuming we don't miss, we are always guaranteed to pick a student. So we have a probability, if the probability of an event is 1, then the event is guaranteed to happen. All right, okay, so let's look at this little PowerPoint slide here, detailing those ideas. Okay, so here, if it's 0, it's impossible. And over here we have the probability of 1 if the probability of 1 is certain. And then it makes sense that it makes sense that the closer we are to 0, the more unlikely that event is to happen. And likewise, the closer we are to 1, the more likely that event is to happen. All right, now here's some interesting other information to know. So let's suppose you have a probability experiment. That's a process that leads to well-defined results called outcomes, and we'll get to those in just a few minutes. And an outcome is the result of a single trial of a probability experiment. So let's look at this experiment right here of tossing a coin once, okay? So here's all the possible outcomes right here. And tossing a coin once is our probability experiment. Okay, so here it is all in detail. Um, the event is going to be tossing a head because we're trying to find the probability of tossing that head. Okay, well, here we have something called a sample space. A sample space is a list of all the different number of possibilities we can have, okay? So again, a sample space is a list of all the possibilities that we might get for a particular experiment. So in this case, if we toss a coin, well, the possibilities we may get is a heads, H for heads, or tails, T for tails. So let's suppose you want to find the probability of tossing a head. Okay, so in this case, my event is tossing a head. And to find the probability, well, in the last examples, we put the letter inside the parentheses, but there's nothing wrong with putting the event directly inside the parentheses. And so P parentheses head means probability of tossing a head. And notice that in the sample space, we have two possibilities right here, and only one of those is head. So we get a probability of 1/2. So H is one possibility out of a total of two possibilities. Okay, now maybe many of you like Dungeons and Dragons. Okay, I used to play that when I was a kid until my parents broke us up, found out what we were really doing in the room. Okay, all right, so okay, so let's talk about so in Dungeons and Dragons you might see this 20-sided die. Okay, now we call that a let me look this up. Let's find out what this is called. Let's go to Wikipedia. All right, I know what it's called now. It's called an icosahedron. Okay, so if you have 20-sided die, we call that an icosahedron. And here's a nice, beautiful, convex, regular icosahedron right here. Okay, isn't that beautiful? So gorgeous. Made up of a bunch of triangles put together. All right, okay, so if we're rolling a die that's a icosahedron die, we get 20 possibilities. So here's the sample space for that. And let's suppose that we want to roll a number greater than 16. So here, we're trying to find the probability that we roll a number greater than 16. Right, and so just look at the sample space here and just count how many numbers are greater than 16. We have 17, 18, 19, 20. There's 4 numbers greater than 16. And so the answer is 4/20, which is 1/5. And that's going to be 0.2 or 20%. So that just simply means out of all the numbers on the die, 20% of them are greater than 16. Okay, now let's suppose you want to play some cards, right? Okay, so it's also good to know some information about cards like we see here. So there's 52 cards in the deck, and as you can see, the top there are hearts, which is one suit. The second row is diamonds, which is another suit. The third row here is clubs, which is another suit. And the last row here is spades, which is another suit. So there are a total of 4 suits. And we have the denominations ranging from ace to 10. And also we have some cards on the right here. So you see the queen, the jack, and the king. Those have faces on them. So those are called face cards. And so as you can see, there's going to be a total of 12 face cards, 3 of them per suit. Okay, so let's suppose you want to do this problem. Let's suppose you wanted to find the probability of choosing a queen. So if you look back in the slide there, there's actually a total of uh, 4 queens in this column right here, right? So we get the answer of 4 over 52, which is about 7.69%. Let's suppose you want to find the probability of not choosing a queen. There's 2 ways to do this one. Okay, we have way number 1. Way number 1 is to simply just count up how many of those cards are not a queen. Well, looking back the slide there, okay, well, there are 4 queens, right? Which means the rest of them are not queens, which is going to be 48 cards, okay? All right, so we can do a 52 minus, take out the 4 queens. 52 minus 4 is 48. And so the answer is 48 over 52, which is going to be 1%. It's roughly 92.31%. Okay, so if you don't like queens, you have a pretty good chance of it happening because 92.31% is pretty darn close to 1. Okay, so the probability of choosing a queen, as we saw earlier, was about 7.69%, which is pretty close to 0%. And so it's pretty rare to pick a queen. But if you don't like to pick a queen, you have a pretty good chance of that happening. Okay, let's do way number 2. For way number 2, the idea is to start out with all of the cards. There's all the 52 cards. And we know that 4 of them have queens, right? 4 of them are queens, okay? Now, basically, in a deck of 52 cards, either you are a queen or you are not a queen. And so we'll put the queens here, which are just 4 of them in this deck, in this space right here, which means the other section here will be not Q. Okay, now here's the idea. So what we'll do is we're gonna start off with the entire 100% of all the cards. And if we take away all the queens, we'll be left with all of the non-queens. And so we'll do 100% minus, okay, there's how many queens are there? There's 4 queens, 4 out of 52. So that's going to be 1 minus 4 over 52, which again leads to 48 over 52. Again, roughly 92.31%. All right, so here's basically what we did. To find the probability of not something, we do 1 minus probability of that something happening. Here's a formula that describes that. So we have for any event E, if E prime is the event E does not occur, then P of E prime is equal to 1 minus P of E. And note that E prime can be thought of as the negation of E. Negation of E just simply means the opposite of E or not E, okay? All right, so if we do the same problem again, we'll set E equal to picking a queen. And we want to find the probability of picking not a queen or not picking a queen. So that'll be P of E prime is equal to 1 minus P of E. And so P of E prime is equal to 1 minus P of E means the probability of picking a queen. That's 4 over 52. And so again, we have 1 minus 4 over 52, which is 48 over 52. This time, let's just keep it as a fraction. So if we reduce this fraction, it's going to be 12 over 13. Okay. Now let's look at a more complicated example. Well, actually, not yet. We'll look at another example right now, and then we'll look at a complicated example after that one. Maybe you're saying, well, they're all complicated. What are you talking about, Tisher? Let's just use this table. All right, now what's going on here? The statement is, I believe men and women at my company are paid equally for equal work. And let's suppose we said this to a group of men and women, and here are the responses right here. Okay, so let's find the probability of picking a man who agreed. Well, before we do that, we have to figure out the totals of each of these rows and columns. So in other words, we're going to find the total of how many agreed, the total of how many disagreed, the total of how many said not sure, as well as the total of all the men and the total of all the women. We've done that before. We've done that in some time ago, and here are the results for that. All right, okay, so we're going to find the probability of having a man that agreed, right? Okay, so all right, so it looks like here that 973 men agreed. And we want that out of the total of everybody. Okay, now we have a bunch of totals here, but we want the total of everybody, whether they're men or women or however they responded. And that total is right here, which is 2,494. And so we can say that the P of, we can say P of man who agreed is equal to 973 over 2,494. Now, let's suppose you want to find the probability of a man who did not agree. Okay, now again, we can use a formula we saw earlier with the P of E prime, or we can just count them out. Either way is fine with me, but maybe it might be easier to use the formula in this case. So this time we'll let A equal man who did not agree. And so we'll have P of A prime is equal to 1 minus P of A, and that's going to be equal to 1 minus P of A, that's 973 over 2494. And working out the math, it gives us about 0.6099. Now let's do this next problem with the same table that we're working with right now. Let's suppose that we want to do, say, if a person disagrees, or let's say if a person agrees this time, then what is the probability that the person is a woman? If a person agrees, then what is the probability that the person is a woman? Right now, this time, we're limiting to who we're choosing from, okay? So this time, we're limiting to who agrees, okay? In other words, we just want all those people who agree. So that's going to be our denominator. So how many people agreed? Well, let's find out. So if we look at the table here, a total of 1,721 agreed. So that's going to be our denominator for this one. Okay, so what this means is out of the 1,721 people who agreed, how many of those are women? Well, let's see, that's going to be 748. So the answer for this one is 748 over 1,721. Okay, now, by the way, anytime you see the word if, it's conditional, so we call this conditional probability. So conditional probability is useful if you perhaps want to concentrate on a certain demographic like men or women, for example. So in honor of that, let's do another problem. Let's suppose if the person is a woman, what is the probability that the woman is not sure? All right, so this time we're limiting our total to just the women. So let's see how many women there are according to the table. Let's see, looks like look at the table, there's 1,247 total women. All right, so it boils down to, out of those 1,247 women, how many of those were not sure? And we get 112. So 112 were not sure. So the probability is 112 over 1247. Now let's do this complicated problem I was telling you about earlier. Instead of flipping one coin, let's flip a coin twice. Or we can think of this as flipping two coins either way. Okay. So if a coin is flipped twice, what's the probability that we get two heads? Okay, now in order to do this one, in order to do a more complicated problem, I strongly recommend writing out the sample space. And again, the sample space is the list of all of the possible, a sample space is the list of all the possibilities that we incur. Right, so in this case, now by the way, in order to list the sample space, there's many ways to do this, okay? We can list this in the form of a set, and a set is just a collection of objects. So in this case, we're going to talk about the collection of all the different possibilities. And to list them, we can use these braces, we can use these symbols here called braces, okay? All right, so the ways are, we can have HH, okay? Now again, we're talking about the sample space of all the different ways of flipping a coin twice, okay? So we have HH is one way, that is, we'll do heads the first time, heads the second time. Another way to flip a coin is HT, so that's going to be heads the first time, tails the second time. Another way is to flip the coin to TH, or flip the coin, TH. So tails the first time, heads the second time. And also we have TT, tails the first time, tails the second time. Okay, so this is the sample space of flipping two coins. Once you have your sample space, now we can use that sample space to find any kind of probability problem pertaining to that sample space. All right, so in this case, the problem is, what is the probability that we get two heads? Well, if you look at the sample space, there are 1, 2, 3 different, or 3, 4 ways, right? There's 1, 2, 3, 4 different ways to flip a coin twice. And out of these 4 ways, only one of these ways is HH, which is getting two heads. And so we can say that the answer is 1/4. So we can write probability of getting heads, getting two heads is 1/4. And 1/4 is closer to 0, so more than likely we probably won't get two heads, but let's try. All right, now in my hand I have a nickel right here, and you can see Mr. Thomas Jefferson right there as the head there. Okay, you can see him right there as head, and we have tails on the other side right here. Okay, so let's flip this and see if I get two heads. Oh, I got a head right here. Yay. Let me flip it again. Oh no, I got tails. Oh, I got tails right there. So I'll try again some other time. Okay, let's do another problem related to the sample space. If a coin is flipped twice, what is the probability that we get the same outcome each time. Okay, let's go back to sample space again. Okay, now by the same outcome each time, I mean, okay, whenever you flip one time, you want to flip the same thing the second time. Well, do that. We either can do it with HH or TT. So the answer is going to be 2 out of 4 or 1/2. Okay, so out of the 4 possible ways to flip a coin twice, only 2 of those ways will give us the same thing on each time of flipping it. So it's going to be 2 over 4 or 1/2. Okay, so we get a 50% chance of that happening, which is so-so. Okay, now let's talk about the sample space of other things. Okay, well, before we do that though, I wanted to tell you all the different ways of doing a sample space or listing a sample space. Okay, so here's the ways of listing a sample space. Okay, one way is to use the set notation like we just did. Another way is to make a table. And here's how we do that. Okay, so we want the, let's put the first flip on the row here, the top row, H and T. And we'll put the second flip in the column heading over there. Okay, now we do this like we fill out a multiplication table. So remember multiplication tables back in the elementary school? Well, we're gonna do a multiplication table right now with H and T. So you have HH, that's gonna be HH, that's gonna be 2 heads. We got H right here and then T up here, so HT, and then T right here, H over there, so TH, and then TT right here. Okay, so to get the outcomes, to get the sample space, we can also make this table like we just did. And here's the finished product right here in better form. Another way to make a sample space is to use what's known as a tree diagram. So we can make a tree diagram. And here's how we do that. Okay, now by the way, again, to clarify, for the table, this is the first time, we'll say. Put the first time in the row there, and the column here the second time. Okay, for the tree diagram, we'll put the first time right here. And on the first time, either we get an H or a T. We'll put the second time over here. Okay, now if the first time is H, we could also have an H, so this refers to HH. Okay, now if we get H the first time, we could also have T the second time, so that'll be HT. Now we could have T the first time, which means we'll have H the, which means we could have H the second time, so TH, and then we could have T the first time and also T the second time. That's going to be TT. Okay. Now, when you have when you have a really large number of possibilities to go through, a tree diagram and even a table can get very long and laborious and time consuming. And so feel free to use whatever way works for you. You can make a tree diagram, you can make a table, or you can use the set notation like we did right here in this example in order to make the sample space. Okay, now let's get more practice in making a sample space. All right, so suppose an icosahedron die was rolled and a coin was flipped. Actually, let's do a regular die. A six-sided die was rolled. Make the sample space. Okay, let's go ahead and just use the set diagram for this one, or set notation for this one, okay? Now, let's suppose that we just have letters on the icosahedron die. Now the icosahedron die is 20 sides, and so let's suppose that each side is made up of the letters A through T. Okay, so we have the letters A through T on each side. And so we can have A on one side. Now at the same time, we're going to roll a six-sided die. Let's just say we have numbers 1 through 6 on that die. So again, we have letters A through T on the icosahedron die, and we have numbers 1 through 6 on the six-sided die. So we can have A1. A1 means roll A on the icosahedron die and 1 on the six-sided die. Or we could have A2, A3, A4, A5, and A6. All right. Now, we could also have a B1, a B2, B3, B4, B5, and B6. And as you can see, this will take a lot of time, right? But it may be well worth it depending on what kind of probability problem that you're dealing with, okay? Right, but you get the idea, right? We have C1, C2, C3, C4, C5, C6. Again, clarifying, C6 means roll a C on the icosahedron die and a 6 on the six-sided die, okay? Now we can put dot, 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 okay? And the letter right before T is S, so we can say S1, S2, S3, S4, S5, and S6. And then finally T1, T2, T3, T4, T5, and T6. So those dots I put mean I omitted some of the examples that are between C and S there. With that, how many possibilities do we actually have in this situation? Well, I'll leave it to you to figure that out. Let's get more practice on using a sample space to get the answer to the problem. By the way, here's the tree diagram for the two-sided die there. Now let's do another problem, okay? This time, let's roll a red die and a blue die. And here's all of the possible ways to do that. In this, and here we see a nice little table being used for that, right? So a table works pretty good for that one, okay? Okay, now suppose you wanted to find the probability of rolling two dice where the first die is 3 and the second die is even. Well, again, we just figure out how many possibilities there are, or what the possibilities are in this case. So we got 3 and 2, 3 and 4, and 3 and 6. So what's the probability? Well, it's going to be 3 over. And how many total possibilities do we have? We have a total of 36 possibilities. So 3 over 36, which is 1 over 12. Okay, we'll do all three of these examples. So given that we roll a blue die, given that we roll a blue die and a red die, was probably that the sum is 8. Right? Well, let's see. So we have let's see, 2 and 6. 2 plus 6 is 8, so that'll work out. So if I want to roll a 2 on the red die and a 6 on the blue die, that'll work out because 2 plus 6 is 8. So remember, sum means plus. Okay. And how else can do it? How else can we do it? Well, we have 3 and 5, right? You need to have 4 and 4, 5 and 3. Now notice that 3 and 5 and 5 and 3 are not the same thing. Okay. And then 6 and 2. And so we have 5 out of 36 ways. 5 over 36. Okay, now suppose we want to get the same number on both sides, which is called doubles. Okay. Well, we have 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and 6 and 6. That's going to be how many ways? That's going to be 6 out of a total of 36 ways. So the answer is 1 over 6. And finally, find the probability of a sum less than 5. Well, I've already highlighted those numbers, those possibilities where you get a sum of 5. And there's 6 possibilities. Okay, and this is very, very beautiful because, you know why it's so beautiful? It's beautiful because we get this nice triangle here. And there's 6 possibilities, and because it makes a nice triangle, 6 is called a triangular number. So 6 over 36, which is 1 over 6.